In March 2015, I gave a session on the value of information using the URSA minor movies problem. It discussed how scenario maps could be used to conduct VOI, but using perfect information. And in that video, I make a comment that you can also assume imperfect information on the scenario maps. This video is a follow-up to that video where we're going to be focusing on imperfect information and show how the imperfect information changes the results. This particular analysis is being done only in SIPMath and not using SDA. As a review, value of information is added by making a change in decision. The VOI is typically considered to be the EV of the project with the additional information, less the EV of the project without the additional information. And then we can calculate this using any value measure such as NPV or value creation. Remember, we can't do this with rate of return. We need to remember in conducting VOI to include the cost and the schedule impacts of acquiring the information. In this particular example, we will be including the cost, but we will not have any impact for schedule. Information is useful if it reduces uncertainty, but does not necessarily add value. Quite often, reservoir engineers or project managers want to reduce the uncertainty in the project, but doing so at the expense of gathering information is not attractive unless there's a potential to change a future decision. This value of information, whether perfect or imperfect, is a function of three factors. One is our current understanding of the key reality uncertainties that are important for making an asset decision. In other words, what is the range of resource? If I have a very narrow range, additional information is not going to really help me. The economic impact of future asset decisions, if they should change based on information about the key uncertainties. This is where oftentimes teams get in trouble because they have such a narrow range of alternatives to consider. There can be very little value of information. So considering a wide range of alternatives is actually beneficial to calculating value of information. The third element is the reliability of the information. How do we interpret that test or the information that's acquired? So as a reminder, the URSA minor movie release is going to have to make a decision whether to release a movie that costs $150 million or whether to conduct a preview of the movie to gather information. In this particular problem, the subject matter experts have identified three different scenario maps. There's the good, the okay, and the bad, and they have 40, 40, 20 probabilities. And when those are added together, we get this black line which represents the reality curve made up of these three things. The gross revenue before expenses, that's the 150 million to release it, is 157 with no information. So VOI generally is generated by making different decisions. In the no information case, we have to make a decision whether to release the movie or trash the movie. And in this problem, we've kind of recharacterized the type of information as I can go out to the back lot of the movie theater, pick up some employees and say, hey, come and look at this movie and tell me what you think. That's my sneak preview. It doesn't cost a lot of money, and they indicate whether it's bad, okay, or great. The other alternative is I release the movie to 10 theaters and get survey forms from the people that watched the movie, and they tell me whether it was bad, okay, or great. So this 10 theater information is much better information than the back lot, but it also costs more money. The 10 theaters is going to cost $12 million, where the back lot only costs $2 million. In both cases, I get to make a decision whether to release the movie or trash the movie based on the outcome of those surveys, that pre-release. So how does the reliability differ between the backyard, back lot, and the 10 theaters? In the no information case, the decision is to release the movie. I think we saw that previously with the expected value of 157. That's before tax, by the way. If I go get backlot information at a cost of $2 million, if in reality it's a great movie, I'll see that 50% of the time, and 15% of the time I'll see it as bad. If it's bad, I will also see it 50% of the time, but I'll also think it's great 20% of the time. The 10 theaters gives me more accurate information, but not perfect information. So when it's great, it's 80, symmetrical down here. I guess it's symmetrical the whole way, isn't it? I put reliability here in quotes because I really don't know how to give you a single number about the reliability. So for example, would you be willing to say this is 80% reliable? It's 80% chance of getting the right one here, but whether I get this isn't 20% and this 0. So this somehow has to impact the reliability number that I might quote to you. So I really don't know how to give you a single reliability number for one of these matrices. Okay, let's move in the live model. Sam Savage always likes to have live models, so let's go do that. Here's my model. I've modified it a little bit. I have a dashboard now up front. So there's a dashboard down here, and there's a model worksheet, which is what I typically use. That's where most of the work is done. Got a typical data table, random numbers. So for demonstration purposes, what we're saying is what type of information are we going to gather? We have a choice at none, backlot, or theater. We have to make a decision based on information whether to release the great movie, the okay movie, or the bad movies. So this is the decision I'm going to take based on the indicator, and I can say yes or no to each one of these. I then show you the bottom line and the value of information. Now in this particular case I have none, which is my reference case. Therefore there is no value of information. Scrolling down here a little bit, we see this graph of the bottom line, and you'll notice that this is our somewhat similar to our gross revenue, but it's moved over to the left because I've deducted the cost of release and paid some taxes. You'll also notice that there's two lines on top of each other. That's because the reference case is being plotted as deterministic, and on top of that I'm showing you the current case. We'll see how that moves when we go to imperfect information. And over here we have a histogram distribution function of that revenue. And you'll notice that we've improved the histogram by showing a range here of values rather than a midpoint or something. And down here we have the value of information distribution. Well, because I didn't gather any information, the value of information is 0, so it's just a straight line. And there's no distribution here. Well, let's not worry about that. It's a trivial case anyway. So we've got this 4.5. let's change this to gathering the back lot information. So the back lot, oh, let's go back here. Let's do something here. Let's go to none, and let's just copy this, and we'll put it over here. Just store it away, right? So that's no information. Now let's do the back lot information. So what we can see is that the bottom line went down, and our value of information is actually negative. Why is that? It's because I didn't change any of the decisions. Remember, I can't have any value of information unless I change decisions. So let's change the OK movie to a no, and we'll change this to a no. And so now we've got a 5.1 and a 0.6. So if I just release the great movies, I do have a value of information equal to 0.6. My MPV, or my bottom line, increased by 0.6. This is after tax, considering the cost of the test, which was $10 million. Over here, we can also see that here's the distribution of the bottom line. And remember that we released when we saw a good movie. Doesn't mean there was a good movie. We saw when we thought there was a good movie. And it appears that we thought we saw there was a good movie, about 15% here and 15% here. So it's about 30% of the time. The rest of the time, just 70% of the time, we saw it as being bad or okay, and so we did not release. And that resulted in this 5.1. And we see the distribution here. So what if I now say I release the OK movie? If I release the OK movie, oh, now I've got a 9.1. That's better. Well, that's good. And my value of information is 4.6. So this is the back lot here, right? Clearly, if I don't release any of these, I'm going to lose money. I guess not, because I guess you could tell me that it's never any good. The bottom line is minus 0.3, and I have a loss of minus 5.8. Okay, so let's go experiment with the better information here now. We'll go look at the 10 theaters. I now incur a cost of $12 million to conduct the sneak preview. And once again, I've got a minus 3.3 because I haven't changed any decisions. So let's go through this process again. We'll do the same thing, a no and a no. And even just because of the accuracy of the good, now I'm releasing less often. I'm only releasing 20% of the time, but I'm only releasing good movies. That's because it's more accurate. And you'll see that my bottom line went up to 11.4, and my value of information is 4.6, which is bigger than the 4.6. So this is 10 theaters, good only, okay? I'll just abbreviate it that way, okay? And if I came in here and also did the OK movie, now I'm up to 13.3 and 8.8. So this is 10 theaters, good and okay. All right. Do you think I don't know that we can do any better than that. I've kind of looked at all the combinations. Let's come down here and look at the value of information. So when I look at the value of information, it's 8.8 here, 8.8, okay. So let's dissect this distribution. So there's a note here. It says indicators suggest acceptable to release, no change in decision policy from no information. So when I do the same thing as in the no information case, which is to release all the time, I simply incur the cost of the pre-release. And that's what this is representing. So this is when I make a decision to not release, and the movie would have been bad, and so I save that money. What is happening down here? What is this long tail? That long tail represents not releasing the movie, when in reality it was a great movie or okay movie, and I would have made money. That's the downside, that I don't release the movie, and I would have made money if I had followed the reference case. Let's do something here. Why don't we change this from 10 theaters. In fact, I'll tell you what I'm going to do. I'm going to split my screen here. And we'll change this to back lot. It has more of a downside tail. Let me go back again. It's more of a downside tail. About the same upside, I guess. I don't know. I guess it's a little bit more, maybe more, 20%. Let's see. Oh, no, no, no. 8.8. This is much better chance here. So, all right. Much better. Okay. So let me show you how the model's set up. This is the model part. And this is simply bringing in the information from our dashboard and our decision policy. It picks up the cost of the distribution. I have the distributions, the reality distributions for the great movie, the okay movie, and the bad movies. Okay? And you'll notice they do overlap. In other words, this minimum here for the great movie is less than the maximum for the okay. But you might also notice that the minimum for the great movie is considerably more than the maximum for the bad movie. Then we need to identify our conditional probabilities, and what I've done over here is identified multiple tables of information. So I have a perfect indicator. Remember, this is great. This is the reality here, and this is the indicator. So this is perfect information. Here's no information. And what I did here was saying, hey, I could, if it's a good movie, I think it's great, okay, or bad in the same probabilities as the reality. But I don't see any difference in probabilities. So this is a no information indicator, if you will. And then the back lot, here's the probabilities we showed you on the screen and the slide deck, and here's the 10 theaters. And I can pick the type of indicator I want. Here's that's coming from the dashboard. And then I have my deterministic model, and these results go over to a data table, or I'm picking up certain results up here at the top, I guess. Picking up these results of results of the release, the cost of the pilot, the cost of the release, the bottom line. I picked up the indicator, what the reality was, and whether I released it or not, so I could see the decision policy. And then there was an indicator index. So you just kind of pick up various things, whichever you think might be useful, some of which you may not use. So I think that's about it on that. Let's go back over to our model, our PowerPoint here. So what have we learned? That SIPMath can be more than just a probability calculator. It can add up. It can add SIPs, right? That's what Sam Savage advertises. But it's a lot more than that. We can embed decision policies into our model and actually calculate the value of information using SIPMath. We could have also done this with an SDA tree. We can also do both perfect and imperfect. And the other point I want to emphasize is that VOI is a distribution and not just a single number. I think by using that distribution of value of information and talking to the project team, project manager, DRB, you can better explain where the value of information is coming from and what kind of results they might expect. So I encourage you to consider using a SIPMath approach for your value of information. I think having the ability to look at continuous distributions rather than just 3 points and using a Bayes that's only 3 possible outcomes is far superior. And I think with the SIPMath, you can get the distribution of the value of information. And I do not know how to get that distribution using SDA and a decision tree. So thank you for listening. Until next time.